Hi, everyone. My name is Subha Madhavan. I'm at Georgetown University's Center for Biomedical Informatics, Innovation Center for Biomedical Informatics. So the caveat is I'm a biomedical researcher and not a technologist or an engineer. So I came to this conference to really learn about the trends in big data and especially in technological solutions that can help us in dealing with big data in biomedical research. And you all have not disappointed me. So I'm really glad to be here. So what I hope to do in the next 4 minutes and 55 seconds is really to tell you about some of the challenges we're facing in big data, especially with next-generation sequencing in cancer research and other biomedical research, and also some of the practical solutions that we are leveraging today and would like to learn more about you. So if any of this I speak about today is interesting to you, please stop by at the poster session and we can talk more. So yesterday, a gentleman mentioned that everybody's definition of big data is different. So I just wanted to kind of set the scale up front. So this is the scale we're talking about. So the world's current sequencing capacity is estimated at 13 quadrillion DNA bases a year, which requires more than 3 or more exabytes of storage. So I'm not here to talk about storage. I think we've heard a number of talks about storage. So the real challenge is really analytics. So it's not just about the big data, but how do you go from that big data to really actionable, small clinical information that we can put in front of researchers and clinicians for hypothesis generation and patient care. So the second bullet point here is the NIH-funded 1,000 Genome Study, which many of you may have heard about. If you're keeping your ears plugged into the bioinformatics field, they deposited about 200 terabytes of data into GenBank, which is the largest sequence database that's managed by the National Library of Medicine. In the first 6 months of its operation, this is twice as much of the data that was deposited in GenBank in the past 30 years. And there was a mention of Million Genomes Project, and I truly believe that we are heading very much in that direction. So what are some of the motivating scenarios? So the first motivating scenario for me that makes me wake up in the morning and go to work every day is really, how do we leverage big data for the clinician? So, the whole dream of personalized medicine, so you probably can't see all the details in here very clearly, but the bottom line is, we can extract DNA from your blood, which is constitutional DNA, and help predict the risk for disease, or tell you whether or not you're in risk for hypercholesterolemia 10 years down the road, which will help you modify your lifestyle. So how can we leverage all this big data to really help realize the dream of personalized medicine? So I won't go into the details of all this, but really, when you start out here, you have about a terabyte of information. So that DNA from your constitutional DNA, it's about a terabyte of data. Once you go through all this filtering process, we filter by annotation, we filter by protein function, we filter by whether or not this polymorphism that we found in you is present in a large SNP database called dbSNP. So when we end up doing all the filtering and analysis, we end up with a short list of variants, which is about 32 gigs of data, which is the most useful form of next-generation sequencing information that we want to use clinically. So the challenge is how do you go from here to here in an effective as well as an efficient fashion. So if you look at the slide here, in 2000, this big block of blue really represented the amount of time, energy, and money that we spent on sequencing itself. And that has really been going down because of technological improvements, so we can do sequencing in less amount of time. But what is really taking up much of our time, energy, and resources is really the analysis, the downstream analysis. Once you get the sequence data, how do you get down to that small, actionable clinical information? So I think the real challenge is how do we go from this data to doing the analysis more effectively. The second motivating scenario, I won't go into more details of this. It's an epidemiological use case of involving public health. So let me quickly run through what are the different levels of data. So this data is not just one big blob. So there are different levels of next-generation sequencing information. There is the level 0 data, which I call as level 0, which is unaligned raw read. So essentially, you write it once and you read rarely. And we have to be very smart about storing the next-generation sequencing information, because think about it. It only costs me about $1,000 to draw your blood and resequence your data. If I stored it, and if I have a 1,000 genome project and I have 1,000 terabytes, it costs me about $50,000 per month. So it's easier to actually resequence the information rather than having to store this information. So then there is level 1 data, which is the aligned read. So here again, you store it once and you read it rarely. And then you have level 2, which is the consensus sequence. So you take the DNA data, you map it to the reference sequence, and you build the consensus sequence. This is, again, read once and write once and read infrequently. And now the data starts to become more interesting with level 3 and level 4 information, which is really the actionable information. So some of the practical solutions we're leveraging is the cloud, AWS, Amazon's Glacier, MongoDB. I like the fact that we don't have to model the data up front because we don't know all the anomalies that we're studying. So having that sort of flexibility helps us store this information and read it. I'm not going to go into the details of this. Smart visualizations are required. So really, baby steps from big data to actionable information. Need better visualization techniques. Need smart and parallel processing. Not the type of parallel processing that we heard about yesterday, but more sort of, can we divvy up this data more smartly? So for example, we take the 22 chromosomes and we do the processing on a chromosome by chromosome basis, and then it's easier to put all that together. So we need smart parallel processing. Cost is really an issue, and I think we talked about this yesterday. This is our team. You can look us up at informatics.georgetown.edu. If you're interested in this, I'm happy to talk to you more at the poster session. Thank you.